So my name is Martha Koch, and I'm a professor at the University of Manitoba and also a mathematics education researcher. And I've been involved as a researcher on this grade 9 applied math project for the past 2 years, which has really been quite wonderful. We're going to take a closer look at the 5 practices approach, and you've probably heard that term a lot in the last couple of days. And I imagine that some of you may already know about the 5 practices, some of you may already be using the 5 practices from before you came here to the conference. Chris and I thought that it might be a really good topic for a plenary for this conference. And of course, it's not only our school teams that in this project that are finding the 5 practices really helpful. We know that sales of the book have really been quite steady in Canada and in some parts of the US as well. So here's a quick overview of what I'm hoping to include in this session. I'd like to start by talking a bit about the reasons that I think many teachers are finding the 5 practices really helpful in their classrooms. And then we'll take a closer look at each of the 5 practices. And then towards the end, since I know that some of you are involved in planning math PD opportunities in your schools or in your boards, I want to end the session with a few ideas for how you might use the 5 practices in that way. So I actually first heard of the 5 practices back in 2008 when I read the article that you see here on the screen. And it was the title of the article that really grabbed my attention. So that, in particular, that sort of subtitle, the idea of 5 practices for helping teachers move beyond show and tell. And what kind of intrigued me about that subtitle was I'd been in lots of classrooms where teachers ask students to share their solutions, and they do sort of use a show and tell approach, giving each group a chance to explain their work and share their math thinking. And it seemed to me like a pretty good way to do things. In fact, I was kind of doing the same sort of thing in my teacher ed classes. So I kind of wondered, like, what are the authors getting at here with this idea of moving beyond show and tell? But after I read the article, I could really see how using the 5 practices would help teachers. And in my case, I was particularly at that time thinking about beginning teachers, engage in that collaborative problem solving in their math classrooms, and then in sharing the solutions from that process, but doing so in a much more purposeful way. So I started including the article as a reading in my teacher ed classes and modeling the 5 practices when we were doing problem solving in our classes. And it seemed to work really well. But of course, teacher ed classes are quite a different group than high school classrooms. And I sort of wondered if practicing teachers would also find this approach as useful. So when the book came out a couple of years later, I decided to use it as the basis of a summer course I was teaching for practicing teachers. And these were about 20 teachers in grades 1 to 12. This was in Winnipeg in Manitoba. And that also seemed to go quite well. It didn't matter what grade the teachers were teaching, they seemed to think it was really useful. And I was kind of pleased that one of the benefits of it was that we could use one problem in the room. And these teachers who were teaching grades 1 to 12 all found the problem relevant and beneficial in terms of their own learning and their own teaching. So because that had gone so well, I decided to use the approach again as the basis for a 2-year PD initiative in a school division, a division-wide initiative in Winnipeg. And in this initiative, I'm working with 24 grades 7 to 12 teachers, and we're just about to start the 2nd year of the project. But the 1st year of the project went very well, and I'll be sharing some of the things that those teachers shared with me about their impressions of working with the 5 practices. So let's take a quick look at the 5 practices. This graphic comes from the 2008 article, and you can see that each of the practices is described with a single word, which I think is good in the sense that it makes the practices easy to remember, but in some ways it's maybe not such a good thing in the sense that it kind of hides how much thinking and doing is really packed into each of these practices. Okay? So each of those words is a verb, and it's a verb, unlike the verbs we looked at yesterday from the curriculum, which students are supposed to be doing. These are verbs that suggest things that teachers might be doing in their classroom. And I think in essence that the 5 practices provides a structure that really helps teachers as they are engaging in collaborative problem solving with their students and then sharing their students' solutions in a more purposeful way. And that's where that idea of kind of moving beyond show and tell comes in. And the purpose is really around exploring important mathematics ideas that come from the curriculum. I also really like the way this particular graphic shows very clearly how the 5 practices are kind of a nested set of actions. So one thing builds on another. And when you put the practices together, the 5 of them really work. So I'm going to talk about each practice in more detail in a few minutes, but before I do that, I just want to talk a bit about why I think it is that so many teachers are finding these 5 practices so worthwhile. As I said, the book's been a bestseller for NCTM, and many of the teachers I've worked with have found that it really sort of shifted their thinking and had a big impact on what they do in their classrooms. So I wanted to better understand why this might be. Sort of the researcher hat kind of comes in, and I'm curious about what's going on. So I spent some time analyzing the book and talking with the teachers and other mathematics teacher educators who had been using the resource, and I've come up with sort of a bit of a hypothesis that I want to share with you. So I think that the reason that the 5 practices is so effective is because it helps teachers with some of the challenges that they face every day in every math classroom. So it's kind of my informal hypothesis that there are 4 specific math teaching challenges that are much more manageable when the 5 practices are being used. So these are the 4 challenges that I'm thinking about. So we know there's a big focus on problem solving in mathematics education. Mathematicians describe problem solving as the heart of mathematics. And there's lots of research demonstrating that having students engage in problem solving helps to deepen their understanding of math concepts while building their math skills, and that it can also increase their confidence as mathematical thinkers. So it's not surprising that many curriculum documents, not just the ones in Ontario, but all over the world, place quite a strong emphasis on problem solving. The Ontario curriculum describes problem solving in the way you see on this slide as the mainstay of mathematical instruction. And the quote you see there comes from the 9 and 10 curriculum document, but that same statement is included in all the Ontario math documents. And if we look more closely at that 9 and 10 curriculum, the one that you have on your table there, it's only a 65-page document, and you might be surprised to learn that the phrase problem solving actually occurs 44 times in the document. And if you look just at the grade 9 applied course, 4 of the 9 overall expectations require problem solving, and at least 16 of the specific expectations specifically require students to solve problems or pose problems or work with a realistic situation. And of course, problem solving is one of the 7 math processes in our curriculum as well. So the curriculum, no surprise to anyone in this room, suggests that there should be a lot of problem solving happening in our classrooms. But the question many teachers I've worked with ask is how? How do I bring more problem solving into my classroom? And maybe even more importantly, how do I do problem solving in a way that ensures that I'm covering the curriculum? And so what I'm finding is that many of the teachers that I've worked with the 5 practices are having this experience where using this helps them to answer those how questions and increase their focus on problem solving. So this is a comment from one of the teachers in the PD series that I'm doing in Winnipeg. And as you can see, she's just not sure how to do more open-ended problem solving in her classroom. So she's kind of fallen back on using pretty simple word problems instead. And I think a lot of teachers share this concern and are kind of reluctant to use open-ended problems. One reason is that they aren't sure what they might do if students come up with those unexpected responses, which we know definitely happens when we use these kinds of problems. And I think a lot of teachers are afraid that they won't cover the curriculum if they use up that time on open-ended problems. And the teachers I worked with also had these concerns, but again, they found that the 5 practices provided a structure that helped them with that. So many of these teachers have begun using problem solving throughout their units. As you see in this quotation, rather than only introducing problems at the end of the unit, they're actually using the problems to teach the concepts right from the very beginning, something that they hadn't done before. So I would say a focus on problem solving is built right into the 5 practices. And I would also say that of the need for differentiated learning. So we know that the need for differentiated learning experiences in math classrooms is another dimension of teaching that many teachers find a bit challenging. We know all students in any one classroom have had very different math learning experiences, and they're each thinking about things in very different ways. I know that teachers in each of the OAME Grade 9 project teams commented many times on how diverse the students are within each Grade 9 applied class, and I expect you all have similar observations in your own settings. Here's a sentence from the curriculum document that says, teachers need to draw on the knowledge and skills students have acquired in previous years, assess where students are in their mathematics growth, and bring them forward in their learning. I sort of think that's one of those easier said than done things, right? Especially when our students have very different prior knowledge and skills. So the question for many teachers again is how? How do I make that happen? How can I plan those learning activities that are going to achieve this kind of a goal? And again, many of the teachers that I've worked with are finding the 5 practices helpful for this differentiating aspect of what they do. So this teacher commented on how valuable she found using tasks that have what she calls multiple entry points. So she was using those in a 5 practices framework. Some people will talk about tasks that have a low floor and a high ceiling, whatever expression you're using to describe them. These are tasks where everyone, each student, no matter what their background is, has a way of getting started. There's just something you can do as soon as you read the problem. And then they can move forward with their thinking and with your support. So the way I think about it, using these kinds of tasks within this 5 practices framework means that 5 practices has differentiated learning built right in. And I would say the same thing about facilitating communication. So it's built right in. The NCTM Principles to Actions book, I think Chris mentioned it yesterday, identifies 8 characteristics of effective math teaching. And of course, one of these is facilitate meaningful mathematical discourse. And I think that makes a lot of sense to most of us, that communication helps build students' understanding of math ideas. It helps teachers have a sense of what students are thinking, right? So that they can give them a prompt or ask them a question to move their thinking forward. And of course, communication is one of the 7 math processes. It's also one of the achievement chart categories. So this is something teachers need to be doing all of the time. And it's not always easy to find ways to get students communicating, especially grade 9 students, right? And then that last math teaching challenge that I think is addressed very well within the 5 practices is that the practices have a set of strategies for using formative assessment built right in. So the practices provide a structure for observing students' work, for responding to their work in ways that can push their thinking a bit further. So that's kind of my theory about why teachers are finding this so powerful in their classrooms. But let's take a look at the practices themselves. So the first practice is called anticipating. And actually, as soon as you open the book, you'll see that the authors have actually added practice 0. So there's 5 practices plus practice 0 in the book. And that practice 0 is setting a math goal and selecting an appropriate task. So we're going to just assume that your math goal is going to come from the curriculum. And also maybe that it might include both kind of a math content goal as well as perhaps one of the math processes as a goal as well. So assuming you've got a goal in mind, the next thing that you would need to do as part of practice 0 is to find some tasks that might work for the goal that you have in mind. So where can you find some of these tasks? So you've probably heard some great sources in the time that we've been together for this conference. The teams are using lots of great, a variety of great resources that you might find helpful. But I want you to consider maybe the idea of actually rebuilding textbook problems that you're already using, okay? So that might sound like a lot of work, but I'm going to play you a short video clip from Dan Meyer, and I'm hoping that he might convince you that this is something that might be easier than you think.
So 90% of what I do with my 5 hours of prep time per week is to take fairly compelling elements of problems like this from my textbook and rebuild them in a way that supports math reasoning and patient problem solving. And here's how it works. I like this question. It's about a water tank. The question is, how long will it take you to fill it up, okay? First things first, we eliminate all the sub-steps. Students have to develop those. They have to formulate those. And then notice that all the information written on there is stuff you'll need. None of it's a distractor, so we lose that. Students need to decide, all right, well, does the height matter? Does the side length matter? Does the color of the valve matter? What matters here? It's such an underrepresented question in math curriculum. So now we have a water tank. How long will it take you to fill it up? And that's it. And because this is the 21st century, and we would love to talk about the real world on its own terms, not in terms of line art or clip art that you so often see in textbooks, we go out and we take a picture of it. So now we have the real deal. How long will it take it to fill it up? And then even better is we take a video of someone filling it up. And it's filling up slowly, agonizingly slowly. It's tedious. Students are looking at their watches, rolling their eyes, and they're all wondering at some point or another, man, how long is it going to take to fill up? That's how you know you've baited the hook, right? And that question off this right here is really fun for me because like the intro, I teach kids, because of my inexperience, I teach the kids that are the most remedial, all right? And I got kids who will not join a conversation about math because there's, like, someone else has the formula. Someone else knows how to work the formula better than me, so I won't talk about it. But here, every student is on the level playing field of intuition. Like, everyone's filled something up with water before. So I get kids answering the question, how long will it take? I got kids who are mathematically and conversationally intimidated joining the conversation. We put names on the board, attach them to guesses, and kids have bought in here. And then we follow the process I've described. And the best part here, or one of the better parts, is that we don't get our answer from the answer key in the back of the teacher's edition. We instead just watch the end of the movie.
Okay, so if you're interested in seeing a little bit more about some of the ideas that Dan Meyer shares in that video, and some of you may recognize it, I know it's been around for a little while, that's part of a TEDx talk that he did, and that's available on YouTube for you. So, the anticipating process, it's one of those ones that's kind of deceivingly, it sounds really easy, right? You just anticipate how students might, do the problem. But there's quite a bit more packed into it than that. So first of all, you're going to anticipate how students might interpret the problem. Think about the problem context and that sort of thing. And you might want to change the 36 fences context a little so that it's not so rural. I mean, we can have fences that are being created for music, concerts or for whatever sort of area that you're trying to create for any reason. So anticipating how students might interpret the problem is important. Also, anticipating the strategies and tools that they might use as they solve the problem, partly so that you can have some of that on hand as they get started with the solving of the problem. You'll want to anticipate the correct solutions, the variety of correct solutions that students might come up with, and you'll want to think about efficient strategies, less efficient strategies, misconceptions students might have, incorrect or partial or less efficient solutions that your students might be using. So it's important also, I think, to consider kind of how the anticipated strategies and solutions relate to that math goal you have in mind. And a number of teachers have told me that they had a goal in mind, they got well into the anticipating process, which is before you share it with the students, and they actually realized that it wasn't as good a fit for the goal they had, and they chose a different goal or switched the problem. So there's some back and forth between the goal setting and the anticipating stage as you use the 5 practices. The last thing that you really want to try to anticipate is some of the questions or the prompts that you might use to help students who get stuck when they're engaged in the problem solving. And anticipating that is really a powerful tool for making things go a little bit more smoothly and for pushing students' thinking toward that goal that you have in mind. Because remember, we're trying to say, how is it that 5 practices helps me use problem solving to actually cover the curriculum? Well, this is one of the ways that it can do that. So here's some advice from the teachers that I've been working with on the anticipating stage of the 5 practices. They say do the problem yourself, do it a couple of times. Also do it with colleagues, preferably from across a range of grades, which is a great way to generate and record a lot of different strategies and solutions. Grade 9 applied students will not always come up with solutions that match the grade 9 applied curriculum. And so you'll be more ready for what's coming your way if you've worked in a across the grades kind of way. Several of the teachers that I've worked with have remarked in there when they give me feedback on the work we've done on 5 practices that they really need to allow that time for anticipating. quite a few of them would come back to the workshops. We had a series of sessions, and they would come back and they would go, I just didn't have time for that anticipating, so I just skipped it. And I really got into trouble in the midst of it didn't work nearly as well as when they had done the anticipating. So they're really finding it valuable, but that they need to set aside the time for doing that. One way that can help you when you're first getting started with doing this, because I know your days are busy and it's hard to find time for all these things, but is to find tasks that actually provide sample student responses. And quite a few of the resources I listed on the slide about ways to find tasks actually do include at least a few sample responses at different grade levels. So some of them will show you a grade 7, a grade 8, a grade 9, response to the same problem. So released items from EQAO as an example. The Enrich website also has sample student solutions at a variety of grade levels, and several of the other resources do as well. So that's kind of a nice way to give yourself a leg up on this anticipating part of what you're doing. I'm going to show you some of the solutions that students have come up with on various occasions. I've used this problem for a number of years, as I said, at a lot of grade levels. Some of them I've actually recreated for these slides, and some of them are the students' actual work. I just want to highlight a couple of things that I see in there, and then we'll go on with the other practices. So in this solution, you'll see that the group started working with rectangles, as you might have done. And then they kind of got into this conversation about would a triangle work, and they were trying to draw that out on the whiteboard, and that kind of created a bit of an issue, which we'll talk about in a minute. And then they had this brilliant idea that they could make these 9 very small pens. You see them at the top there in red, and that each of those little pens would be like a 1 meter wide area, and that their total would be 9 meters squared. So they were sure they had the smallest possible because it was smaller than any of the rectangles that they could do. And it was funny because when they did that little one with the red, the red squares, there was this conversation about, is that cheating? Like, are you allowed to do that? Is that cheating? And I always encourage students to think about problems in lots of different ways. And so, I'd say, well, what do we think? I don't think it is. It's another solution. And kind of opening up the conversation in that way. Here's another one. It's a little bit harder for you to see, but in the upper left corner where I've drawn a bit of an arrow there, you can see that this group actually kind of had a bit of a misunderstanding when they started with the problem. So this idea that 3 times 12 is 36, just came to them right away, and then they got stuck drawing this 3 by 12 kind of shape, and kind of working up to the other rectangles and squares, but they couldn't figure out what was going on with this 3 by 12 shape. And the problem that they had gotten stuck with was that they were using 36 as the area instead of as the perimeter, right? So they kind of crossed those over. So once we got that kind of worked through, as I was doing the monitoring with them, they started to see what had happened with their thinking. And that's something you might anticipate, because the number 36 makes you think of 3 times 12, right? And so you get down this kind of path of thinking where you're actually thinking about area and not perimeter. So we had to go through this step of kind of saying, how many fences are you using? Oh, it's not actually 36 fences. So that's what's happening with that one. Here's another one where the group began with the formula. So that was the first thing they wanted to talk about. I know area is length times width. And then they made a table because they started to realize they could have this whole sequence of rectangles and squares that would work. They decided they'd show their thinking by making one sort of obligatory diagram on the top of the page. Decided right away, we've got the smallest, we've got the largest. And so when I dropped by, I kind of said, oh, I wonder if it has to be a rectangle. Would it make any difference if you used a different shape? And then they sort of got into exploring some of those ideas and keeping thinking going. Here's another solution that some students have come up with over the years. This is another one where using the whiteboard kind of gets them into a little bit of a sticky place because the little squares are great if you're using rectangle representations of the fences, but once you go on the diagonal of the square, you're actually not the same size of fence piece anymore. So that usually comes out in the conversation, and I encourage them to move away from the whiteboard and to move toward using an actual set of coffee stir sticks and fences and building the fence that they're using as an actual model in order to do that. But it's very often that groups move out of the idea of rectangles and start adding sides and trying to figure out what that does to the area. Lots of groups really get kind of pumped about the idea of trying to find the smallest shape, and so they kind of get into thinking outside the box and coming up with all these funky solutions for the smallest shape, right? And so this group, I've had a couple of groups do this sort of starburst look here. They're putting all the fence ends together and then trying to figure out how small that might be when you put 36 of them around like that, and they're pretty sure it'll be less than a meter squared, and that's got to be the smallest that you can do. And then another group they got into a debate. The solution you see on the bottom part of that image, they actually had this idea that they would have the 16, on the long side 16, and they'd have the 2 at either end, but they'd angle them way, way out, and so they get into these ideas of how skinny could you possibly make this, depending on how thick the fences are, and how small would you be. I'm pretty sure it'd be less than a meter squared. We win, right? And so there's this sense of, kind of excitement. It's a basic problem, and yet, there's, I don't know, that competitive spirit kind of jumps in, and they want to find ways to make the shape smaller or make the shape larger. Okay, so as you look at that kind of range of solutions and you think about the goal that we started out with, which was that one from the 9 applied, or those 2 from the 9 applied, you may be beginning to see there's a lot of other connections here. So we could be pulling stuff out of the grade 10 academic, using the idea of solving problems with right triangles and trying to do that to help us with the 36-sided shape. There are lots of different things that we might do. You can even pull it into the grade 12 curriculum. There's just connections all the way across. I've got other slides for grade 4, grade 5, grade 6, so wherever you are, there are connections that work there. So that's goal setting and anticipating. Let's move now, in the time that we have left, into the remaining practices. The monitoring, I've talked a little bit about that. It's really the built-in formative assessment part of the 5 practices. It's paying attention to students' mathematical thinking as they're working on the task, going around and kind of prompting their thinking. It's looking for those potential strategies or representations that students have made that are going to help you move toward that goal that you have in mind. Listening to their conversations, making notes, asking questions, can you explain your thinking here? Or dropping that little, kind of comment that says, oh, I've actually seen bigger ones than that. Do you think you could make it bigger? Just that sometimes is enough to get them rolling. And at this point in the 5 practices, you're already starting to think about which responses you might focus on in the discussion that's going to take place at the end of the session. And again, you're keeping in mind that math goal that you set out with as you started. The monitoring can be a bit challenging for teachers. Teachers tell me to keep track of. You'll find in the book some actual examples of little tables that you can create that will help you with the monitoring process. This is quite a simple one. The strategies that you anticipate are in that first column on the left. So I've jotted a few down that sort of relate to the 36 fences. So that idea that they might have confused area with perimeter. You might be keeping track of how they solved the problem. Did they draw a diagram? You might be keeping track of how many people just did rectangles and how many people did other shapes, etc. Different things like that. In the center column is where you keep track of which group is doing what. And this is just kind of because it's easy to lose track. You've got them, 5 or 6 groups in the room, and you sort of think, well, who was it that had that? Where are they again, right? And this can help you to do that. And then the column on the right is where you might think about the sequence or the order that you're going to explore those in when it gets time to share the solutions. So then the next of the 5 practices is really about kind of selecting which ones of the solutions you're going to share, or which parts of solutions you're going to share. So this is part of that built-in communication, facilitating communication part that I talked about earlier. So one way that I've seen teachers do this is they actually have their monitoring sheet, so they already kind of know pretty much who they're going to choose, but they'll actually ask for volunteers. And then among the hands that are raised, they choose the volunteers that match the list they're kind of already working with. One thing that I think is important to remember is that not all groups need to share every time. And they also don't need to share their entire solution. So when I'm going around, I might say, oh, I really love this part of your solution, the triangles part. Could you talk just about the triangles part when it's time to share? And then I'm jotting down in my monitoring sheet, okay, group 3, triangles part, right? And I know roughly when I'm going to get to that. And they learn that you're going to do this over and over again, and if they didn't get to share this time, they'll get to share, another time. You'll want to ensure that some of the common misconceptions are shared and corrected, and that's an important part of this approach. If a key strategy that you're really looking for your goal doesn't emerge, sometimes I have extra student work that I'll pull out and share and say, oh, some students last year came up with this solution, so I can kind of slide it in there, or I might say that it's my solution, but usually I use students' work. And another great idea that some of these teachers suggested to me, and which I think is also in the book, is that you delay the sharing of any unexpected responses. Just say, oh, and that one I want to give some thought to, we're going to look at it tomorrow. Because you do get some of those coming up for sure, and that gives you some time to kind of work through your own mathematical thinking. Okay, so we're almost to the end of the 5 practices. The sequencing is the second last practice. And that's the idea of kind of putting it in order. So how are you going to do this in order to meet the math goal that you're looking at? Some of the strategies that are suggested in the book chapters include beginning with a strategy that's fairly easy for everyone to understand. Others will begin with a strategy that lots of students used. Some people will begin with a strategy that clears up a miscommunication, particularly, or a misconception, particularly if lots of students had that misconception. It's a good idea to ask your students ahead of time if they'd mind sharing a part of their solution so that they've got a chance to kind of collect their thoughts and think about what they're doing. The last step is really an important one in the 5 practices. It's called connecting. And the goal is, really in the 5 practices is not just that you're going to present this purposeful sequence of solutions so everybody can think of 6 ways to solve this problem. We often hear parents say, well, why do they need 6 ways to solve the problem? It's enough that they think of 1. So we're not trying to share and say, oh, you need to learn 6 ways to solve this problem. We're actually doing it because we want students to actually make connections between a few things in the solutions that are there. So the making connections really is to deepen their understanding of the math goal that you're working with. So some ways that you're going to do that might be to discuss those kinds of strategies that are likely to lead to inaccuracies or mistakes. So ones where you have to repeatedly add or do something like that might not be as efficient or as accurate as ones where you multiply, right? So you can show them those sorts of things. The book actually raises an interesting point and explains that it's a lot easier for students to see the connections between 2 solutions if you, as the teacher, when you're facilitating the discussion, focus on not the differences between the solutions, but the similarities, which is kind of interesting. At first you kind of think, well, isn't it the same thing? But if you think about it for longer, you'll realize it kind of isn't. So you need to focus on what's the same in these solutions. And that seems to be more effective, according to the book, in terms of how to do those connections. I just want to talk to you very briefly, last slide, about using the 5 practices for professional learning and share with you some of the things that have been most successful when I've been working with teachers. So one of the things they really liked was having a chance to read the book chapters before we got together. So I didn't ask them to read the whole book. The chapters are quite short. They have lots of examples. They're very accessible and, sort of in ways that teachers find very appealing. So I would say maybe like read chapter 1 before we have our first session, read chapter 2, or 2 and 3 before the next session. They seem to really think that was helpful for them to do it. I was kind of worried that it might feel like homework, but they actually really found it helpful. So they said, definitely do that again. They really enjoyed doing the math problems. So every time we get together, we actually do a math problem and we model the 5 practices. Sometimes I get them to do the goal setting and then I take it from there. Sometimes I get them to do the anticipating and that's the big focus, or we actually go through a selecting and sequencing and a connecting activity. But they like doing the math, which is probably not a surprise to you. So don't be afraid to include that. The other thing they emphasized, many came back and told me and wrote in the feedback they give me, that they enjoy working with colleagues across the grades. They just see that it's so helpful to see how other people teaching at other grade levels might use the problem, the kinds of solutions they would anticipate. They all photographed or photocopied one another's solutions so that they could quickly get quite a rich bundle of ways of looking at the task in a relatively short period of time. So if you do have an opportunity to extend a professional learning opportunity across some grades, I think it's really, really beneficial. They also enjoyed being able to have a little bank of tasks that they could share and access. The main approach that we used also really seemed to work for people, so I'll just close with that. So what they like to do is get together. First we'd do a task, and this might be in a 2-hour, 3-hour session, and then in the second hour, I'd have them work together to find a task. I'd have brought a bunch of the resources, and we'd all be going online, and they would select a task themselves. They would set a goal, although they would all set different goals because they were in different grades, right? So one would be using 36 fences for their grade 7 classroom, one might be using it in their grade 9 classroom, one might be using it in their grade 10 classroom. And then they would go back to their classrooms and actually do the problem, having done the anticipating together, and then come back a few weeks later for the next session and talk about their observations in the different classrooms. And they would bring their examples of student work. And this seemed to be a very simple structure that they really found helpful in terms of using the 5 practices and kind of digging a little deeper into how these practices work and into the kinds of things that take a little more time and energy with the 5 practices, finding their way to do that. There's also a whole chapter in the book, I think it's chapter 8, that has some other suggestions and ideas for how you might use this in a professional learning context. The book itself, they really couldn't be more positive about in terms of the way it's written. There's a lot of examples of real classroom teachers with real problems and actual statements around, I said this and then I thought that, and the thinking of teachers is right there on the page. Okay, so it sounds like I'm sort of selling the book, which I'm not. I just find that many teachers are finding it very, very helpful. And as I said at the beginning, I think it's because it's got those 4 really built-in ways of dealing with 4 big challenges we all have in math classrooms. That building in differentiation, the problem solving, the assessment piece, and the 4th one, which I can't think of, facilitating communication. So there's just so much of that built into this strategy. So I hope you find it interesting. There are the 2 copies there. One you can take back to your schools and think about possibly using this.